Okay, hello everyone, and welcome to week 2 of Space Science with Spice. My goal for this lecture is to give you some computational methods for solving differential equations, which ultimately will help us animate more complicated physics in Python. As always, I've broken the lecture up into 4 sections, the timestamps for each of which and related links are in the description if you want to skip around, and I'll tell you the prerequisites to skip each section at the beginning of said section. So with that being said, let's jump right into it. Part 1 is going to be the essence of the derivative, and the prerequisite to skip this is if you've already taken calc and understand the derivative conceptually. I'm not going to be teaching any derivative rules. I'm just going to be giving an intuition for what it actually means to take or find the derivative. So if you don't know that, definitely watch this, because the idea of a slope or an instantaneous change over time, or change over time, is going to be really important moving forward in animating physics, especially in the later parts. So if you just Google the definition of a derivative, chances are you'll have this huge equation thrown in your face. And although this may make sense to someone who's been doing calculus for a few years, there's a way more simple and intuitive way to understand it that shows how in the real world we're dealing with derivatives every single day in one way or another. Now, just in terms of terminology, you'll often hear a derivative described as a quote-unquote instantaneous rate of change. But in literal terms, that's a paradox. Change happens over a period of time, but an instant is one moment in time. So how can you have a change at a single point? Well, like for example, I could pose a question. If I gave you a picture of a car that's moving, could you tell me how fast it's going? Obviously not, right? But then how does something like the speedometer of a car figure out the car's speed at a certain moment in time? What does that even mean? And if that question feels like strange and paradoxical, then good. You're grappling with the same conflicts that the fathers of calculus did. But like I was saying before, if we look at the speedometer of a car, that's where we start to find our solution, or the essence of the derivative. So what the speedometer is actually doing is measuring how far the car is going over a very small period of time, say the distance traveled between 3 seconds and 3.01 seconds. Then it computes the speed in meters per second as the very small change in distance, let's call that ds, divided by the change in time, let's call that dt. The d stands for some difference in a value. In this case, s is some random variable we use in physics to represent distance. It has no importance. We're going to switch between s and x and r. Just note that this means distance. And dt, on the other hand, is going to come up a lot in representing some very small difference in time. We're going to use that a ton later on in the course, even later on in this video. So in reality, when we're taking the derivative of something, we're not computing the rate of change in an instant, we're computing it over a very small step in time. And if we wanted to represent this graphically, we can imagine looking at a graph of distance traveled as a function of time. So at 0 seconds, you're at the starting point. At 3 seconds, you're 10 meters ahead of where you started. 5 seconds, you're 50 meters ahead of where you started, and so on and so forth. And we can imagine looking at a graph like this and zooming in really close to some point. Say like before, we're focusing on t equals 3. And when you zoom in, we're looking at this window up here at the top right. And we see that this dt is a very small step to the right, since t is on the horizontal axis. And that ds is the resulting change in the height of the graph, since the vertical axis represents the distance traveled. So ds dt, or ds over dt, is something you can think of as like the rise over run slope between two very, very close points on the graph. Of course, we can apply this to any other point in time on the graph. So we consider this expression, ds over dt, to be a function of t, meaning something where I can give you some time t, and you can give me back the value of the ratio at that time, which is the speed or the velocity as a function of time. And just to show you again, taking the derivative of a function is essentially starting at a point and finding a very, very small difference in position, or ds, over some very, very small difference in time, or dt. And we do that in order to find a line that essentially represents the slope of the graph at some point. Now, just to be clear, as you'll learn in your pure math classes, the actual definition of the derivative is slightly different, but for our computational needs and what we'll be doing later, this will be perfectly sufficient. So for part 2, I'm going to be talking about an introduction to Euler's method, and the prerequisite is that if you've already taken calculus and you're familiar with Euler's method, you could skip this, although I'll try to give you a more conceptual and intuitive understanding of this concept that goes beyond rote memorization that you probably learned in class. So in physics, we pretty much define velocity, which we could just think of as speed for the purposes of this club, as distance over time, as an instantaneous change in position, which, as we just learned, means that a change in position, or dx, now we're going from ds to dx, just stick with it, over a very small step in time, dt. And by the way, the triple equal sign that you're seeing right here essentially means that this is the definition of velocity. It's some small difference in position resulting in some small difference in time. And the difference is so small, the difference in time is so small, that we could call it almost like instantaneous. Now, if we think back to what we just went over, s and x are pretty much just different variables for the same thing because they're both distance, and later we're going to be using r too. But when we zoom really far into the graph, like what we did before, and think of ds over dt or dx over dt, we know that we can approximate it as some linear rise over run. So we can go back to our equation for velocity and approximate it to some actual like change in distance over some change in time. And this is something that we could compute using the definition of change. So if we rearrange this equation a bit by separating the delta x into final position minus initial position, multiplying both sides by delta t, and then adding the initial position to the other side, we end up with this really powerful equation where you essentially plug in some initial position at a moment in time, and then add the velocity or speed of the object at that moment in time times the small step in time, or dt, which can be something like 0.01 seconds, and then you end up with the final position of that object, effectively reversing the derivative. And the reason we could do this, by the way, is because think of velocity as x over t times t, well, the units of second cancel out, and now we're just adding some initial position plus some change in distance, or a change in position will give us our final position. And think back to, I just said this before, remember that if the delta t value is, just remember, keep in the back of your head the phrase reversing the derivative, because we're gonna, again, that's gonna come up again and again as we move forward. Now, remember that this delta t value, we call it dt, is supposed to be really, really super small. And so if this whole thing is going to be the change in x, we're also going to get a really small change in x. But this is where the power of computers comes in. What you could do is that you could feed this equation, the result of it, back into itself by using the previous final position as the new initial position, and then updating the velocity and using the same small step in t, and then repeat this process over and over and over and over again to essentially get a function that effectively evaluates the position of an object based on some initial position and velocity as a function of time. And we can use this process, which is more commonly referred to as Euler's method, to animate our objects in VPython. And as a side note, this is completely unrelated, but this is something to think about during your classes. The equation that we derived is really, really similar to mx plus b, so just rearrange here. So there's just some food for thought. So now we're going to move on to part 3, which is actually applying what we just learned, Euler's method, to physics and VPython. Now you may have remembered that in week 1 lecture, in VPython, I said that we're going to be working with vectors, which are essentially collections of numbers that describe the x component, the y component, and the z component of something, or in other words, a magnitude and a direction. In this example, we have an x component of a +2, a y component of a +3, and a z component of a +5, and those come together to give us this 3-dimensional resulting vector p, representing a position in 3D space, and it has a direction, which is in the positive of all these things, and a magnitude, which is just the length of this vector. So going back to Euler's method, we can take the terms for position and velocity, which are technically actually already one-dimensional vectors because they have a magnitude, which is just the number value, and then the direction, which is either positive or negative, if it's a direction, either right or left if we're thinking about it on the number line. And we're basically going to upgrade these one-dimensional vectors to 3-dimensional vectors, signaled by this arrow at the top. And effectively what this means is that we're just, instead of moving just left and right, instead of being limited to that, we can also move up and down with the y component, or forwards and backwards with the z component, which is going to be very useful because we're going to be working in VPython, which has a 3D canvas like you saw in last week's lecture. So just for the sake of clarity, I'm going to now replace x with r in these next few slides, but know that either way, whether it's x, whether it's r, whether it's s, all of these terms represent the same thing, the initial and final position or displacement of an object. And I'll tell you when I switch these. So now we're going to be doing a lot of math with these vectors. So just to summarize the rules of arithmetic when it comes to vectors, if we take our vectors and expand them, like I said before, we just get three components, x, y, and z, enclosed by these brackets. And at this point, they can just be thought of as a set of numbers. So multiplying a vector, in this case velocity, times a scalar, or just a plain number, in this case delta t, just multiplies or scales each of the three numbers in the vector by delta t. So I've given you the example for v sub x, or the x component of the velocity. The new x component just becomes v sub x times dt. And adding two vectors, in this case the initial position, when we're adding two vectors, in this case we're adding the vector, the initial position, plus the vector that you get from doing v times dt, and that's just adding the corresponding components of each vector, the x, y, and z components. For in this example I've done it for r sub x, we take r sub x plus v sub x times dt. This is the first, or x component, of both of these vectors, and then we just add them together to get our new x component of our vector. And now what we can do is that we can begin to apply this knowledge to our code. And I'm going to go over this program line by line so you know what the computer is going to be thinking through. So on line 3, we're going to be making a sphere that starts at the origin. It has a color and a radius, and it's going to be making a trail as it moves. You'll see what this means. You'll see what this means when you run this. And then we store the sphere in a ball variable so we can access and change it later. On line 5, we create a variable for time starting at 0, and on line 6, we make a variable for some small step in time, dt. In this case, it's 100th of a second, which corresponds with the delta t that we use in Euler's method. On line 8, we make a loop that will keep going as long as time is less than 10 seconds. And on line 9, we use the rate function to specify the number of loops we want per second, or the number of frames we want per second. And since dt over here is 100th of a second, running at 100 loops per second means that we'll be moving at real time, and 1 second in the program is going to equal 1 second in real life. On line 11, we update the velocity vector. Notice how I said update, because this assignment is going to be happening every time the loop runs, or 100 times a second. And we're going to essentially be making, for this velocity vector, we're going to make the x component of the velocity equal to the current time, which is a changing value. Depends on the current value of time, meaning that at 1 second it's going to be moving at 1 unit per second to the right. At 2 seconds it's going to be moving at 2 units per second to the right and onwards. We're going to be making the y component of the velocity constant value, meaning it will always be moving at 1 unit per second upwards regardless of the time. And we're going to be making the z component of the velocity 0, meaning the distance isn't changing on the z-axis, meaning it's not moving forwards or backwards. And pause for a second if you don't understand this, because it's really, really important to understand what this line 11 means and how the velocity is going to be changing in some respects, but also constant over time. So moving on to line 13, this is where we implement our Euler's method. Remember that in Python, when we have a single equal sign, we evaluate the right side first. So we have the current, or initial position at the moment of the ball, plus the velocity at the current moment, times a small step in time. And according to our equation, for Euler's method, that gives us our final position, which we then store as the new, or final, or updated position vector of the ball. And notice how we didn't have to separate these vectors into their x, y, and z components, by the way. Like I said in the math with vector section, you can just add and multiply vectors, and Python will discriminate between the x, y, and z components for you. Now finally on line 15, we're just going to be updating the time to increase by some small but finite value. So now if we go to our code, this is the same thing that you saw before, and we run it, you could see that in GlowScript we see our ball moving for 10 seconds. The x component of the velocity is increasing with time, which is why it ends up going so far out in the x direction. The y component of the velocity is constant, so the ball is constantly going up to 1 unit per second. And if we turn it, we see that the z component of the velocity being 0 made it so there's no change in the position in the z-axis. Now, if we edit this program, and let's say we do something like change the velocity vector, and we replace the x, we exchange or swap the x and the y components of the velocity. So instead of 1 time, it's going to be time 1. Actually, pause for a second and predict what do you think was going to happen. We just changed the x and y components of the velocity. We saw that before it kind of went on like a sideways arc. What do you think is going to happen now? Really pause, and I really want you to make a prediction, because getting something wrong, although it feels weird at first, that's the best way to learn. Every time you get something wrong, it's your brain actually growing. I'll zoom in more here, actually. Should be better. Now, if we run this program, we see that now we get our ball. Oops, did I not actually switch them? No, I didn't switch them. You'll see that if we run our program, now what we get is something very similar to a parabola. We've essentially flipped our previous motion across the across our diagonal, and we end up with y equals x squared, which is a paraboloid shape. So in physics, another useful concept that we're going to be going over is momentum. And this is very closely tied into velocity. And momentum is essentially, as you can see by this triple equal sign, it's defined as the mass of an object times the velocity of that object. And we learned how this vector multiplication happens before. We learned how it plays out earlier in our math with vector section. And what we can do is that we can arrange this equation by dividing both sides by mass to find a new way to represent the velocity of an object. Sometimes it's more convenient to use momentum instead of velocity. You'll see why in the next week's lecture, or in next week's lectures. So what we can do is that we can take our equation for Euler's method, and we can substitute momentum over mass in place of velocity. So we have our equation that we had before, and now we're just substituting v for p over m, momentum over mass, which will be the same, which should give us the same exact thing. Now here's a section of code that's pretty much the same exact thing as what we had before, except for a few differences that are highlighted in red. And I'm going to be going over those. First of all, we made a variable called mass. We set it equal to 1 at the beginning, and we could think of this as mass in kilograms. Within our loop, we commented out, so now the computer isn't going to read this because it's commented out. It's something that only we could see, but the computer just skips right over it. Instead of having a velocity vector, we now have a momentum vector that's going to be equal to the same thing, 1 times 0, x, y, and z. And now, in our Euler's method update line, instead of doing velocity times dt, we're going to have momentum divided by mass times dt. We're essentially just replacing what we said before. And now, if we go to our code and run this section of code, sorry, just let me indent it. Predict what you think will happen. We just added a mass function, but momentum is the same, and our velocity is just a momentum over mass. If we run this, then what we see is that, oh, the color's different, by the way. We get the same thing as we had before. We get a paraboloid shape. And reason for this being is that when the mass is equal to 1, recall that momentum equals mass times velocity. If mass is 1, then momentum is going to be equal to 1 times velocity, or momentum is pretty much going to be equal to velocity. And since our momentum and velocity, our old velocity and our new momentum are the same thing, the same vector, when we replace velocity with momentum over mass, we essentially get the same thing we had before. And recall that mass is 1, so you could also just look at it as momentum over mass, it's just momentum over 1, and we get the same thing as we had before with the velocity. However, the benefit of adding in momentum is not just so we could do the same thing, we can now adjust this mass term. So originally it was 1 kilogram, now what happens if we make it 10 kilograms? And pause for a second and predict what you think is going to happen now. If we have a greater mass of our object, how is the motion going to be affected? And if we run this, you'll see that now our ball is moving really slow. It's moving much slower. And it's not going to go as far either. Before it zoomed way up here and it got way up here, but now it's just barely going to get as far in the same amount of time, 10 seconds. And this kind of reflects how in real life, it's the bigger an object is, the more momentum you need to put to get it to move. You know, like if a bowling ball is coming towards you, you're gonna have to put in a lot. It has like a lot of momentum. It's gonna be really hard to stop it. Versus if a ping pong ball is thrown at you, it's really easy to stop it right away, because although they might have the same velocity, the same speed coming at you, the mass of the bowling ball is bigger, so it's gonna have a bigger momentum, and that's why it's gonna oof you harder. So now, if we go back to our slideshow, what I've done now is I've essentially showed you so far Euler's method for updating the position with a constant velocity. In this case, it is changing, but we're only using Euler's method once, and that's to update the position of a ball. But now what we're going to start talking about is what if the velocity, or what if the momentum over mass, if the momentum of the ball is changing. And what we're going to use then, and this is going to come up a lot in physics, if you're taking a mechanics course, you're going to be talking about this every single day for an entire year, is this concept called force. Now, just to review very quickly, before we defined the velocity of an object, we defined it, see these three things, as some change in distance over some change in time. A small change in, a small step in your position over some very small step in time. Now, what's happening, like I said before, if our velocity is changing? Think about it as a speedometer. We thought of our speedometer as how far you go over how long it takes to get you there, but our speedometer doesn't always exist at one point. Our speedometer changes too. And so that's where acceleration comes in. Acceleration is going to help you represent some changes in velocity over some changes in time. So let's say our speedometer goes from 0 miles per hour to 10 miles per hour. That's going to be some change in velocity, and it's going to happen over time, and that's going to give us our acceleration. And you could, to give another car analogy, you can think of acceleration as the gas pedal, where when you press on the gas pedal, you're going to see the speedometer changing. You're going to see it changing at some rate. Now this equation at the right, F equals ma. We just learned a, that's acceleration. It's just dv over dt. Force now is, you can think of it as some kind of push or a pull. And this equation is Newton's second law, which defines force as the mass of an object times the acceleration, or the acceleration that it's going at. Now, if we take this equation and bring it down here, F equals ma, we know that a, according to this equation, is just dv over dt. So we're just substituting dv over dt in for a, and we're leaving m alone. And now if we bring m into this d, now it's, instead of taking some small difference in velocity, we're taking some small difference in mass times velocity, because you're just multiplying the numerator by this number and adding a parentheses. You might recall that mass times velocity is momentum. And so if we simplify this further, we get our equation, force is equal to some small change in momentum over some small change in time. And you can think of this as the slope of the momentum graph, where time is on the x-axis and momentum is on the y-axis, and the force is taking the slope of that graph at some point. And if we want to start applying this idea where we've gotten a new slope, before our old slope was velocity dx over dt, as you can see up here, we had p over m, which we're using now is just equal to v, which is equal to some change in position over change in time. Before, what we were doing in our first Euler method equation in our code was that we're taking the initial position, we're adding our velocity, or our momentum over mass, times time. That's going to give us our final position. We're updating our position using Euler's method, because again, recall, if this is some change in position over change in time, times time, the time units cancel out, and we're just having some initial position plus some change in position. That's going to give us our final position. Now we could now apply that to, instead of finding a new position, we could find a new velocity or a new speed or a new momentum. And we could use the same identity like we used up here. Velocity is some change in position over change in time. We could do force is some change in momentum over some change in time, or acceleration is equal to some change in velocity over change in time if we take out the masses from each side. And so what we're going to do is that we're going to use the same overall structure of Euler's method up here, where we have our new value is equal to our old value plus a slope times time. We're going to have our new momentum is going to be equal to our original momentum plus some force times our small step in time. The dt stays the same, and the overall structure stays the same. Sorry, stays the same. What we're doing here is essentially force is some momentum over time, and then momentum over time times time, well, the time units cancel out, and we have our original momentum plus some change in momentum equals our final momentum. And now what we could do is that we could start implementing this into our programs to find changing velocities. And this is the same program again as before, but with some changes that I've highlighted in red. So our mass is going back to 1. Our momentum is now constant, because recall that now it's not updating every time in the loop, and it's not dependent on the time at all. The momentum is going to be constant. We're going to have some initial momentum that we're keeping constant. But now, we're no longer, of course, updating momentum in the loop. Now we're updating the force in a loop. Our force is a vector, and we're just going to set equal to 0 in the x component, 1 in the y component, 0 in the z component. And now we're going to apply Euler's method to the momentum. And like we said in our previous slide down here, our new momentum is going to be equal to our old momentum plus a force times dt. And then after we do that, now that we have our updated momentum, this new momentum is going to be used in this equation to calculate the position. And this Euler's method for position is what we did before. And now you can see that when we run this code, let me just copy it in, sorry. Tab all this out. We have all this code, and now when we run it, we're going to get a very similar parabola, except for now it's accelerating upwards. And accelerating meaning we're seeing some change in velocity over change time. And this is the same thing as when we saw the parabola before. Our y component was changing. At first it was 0, and then it was 1, and then it was 2, and then it kept changing every second. Now that we have a force, we have very strong representations of motion in reality. Basically, with just force, momentum, and position, we can represent almost anything in reality. We could represent the spin of planets, we can represent cars moving around, we could represent gravity, we could represent so much stuff. And just as an example, again, if we increase our mass, we can see that again, our ball slows down a ton because it's harder to move. We could set our momentums equal to some negative numbers. So now what it means to set something, to set our momentums equal to negative numbers, is that now our ball is almost being like thrown. It has some momentum in this direction, in this case negative x and negative y, so it's going to be thrown to the bottom left. And now we're going to have a force, which is going to be some push, and we can say that this will be, we'll have a 0 in the x direction, but we'll have a positive, let's say 3 in the y direction. Now the ball is being thrown down and to the left, but it's being pulled upwards with the force. So the result of that is that, oops, this is a fat ball, I don't want that. The result of that is that we have our ball being thrown down, like that. Let's make it even lighter. It's fun to make it a very small value and see it get thrown. We can see that it gets thrown and then it gets pulled way upwards. And now we have some arcing path. We have this kind of curve. And right now this won't let us do much, but as you'll see in the next lecture, this gets very, very powerful when we start specifying what exactly our equation for force is going to be and how we could update that in a more complicated way than just having it be dependent on time. So if we go back to our PowerPoint, we've learned essentially how to update both position and our momentum with the Euler-Kromer method using force. And here's some exercise to try on your own. Again, please, please, please try these exercises. I really don't think watching me is, if you just watch me and think you understood this all, you're very, very wrong. Even I learned something doing these exercises to make sure I had solutions for you guys. Just do these exercises, at least try them. Even if you don't get it wrong, you're going to be learning something, and I will always be there. If you just reach out to me on Discord or email, I'll always be there to help you. So exercise 1 is going to be simulate ball being dropped. So a ball is going to start from a high position, high up in the y direction, and you're going to drop it. And of course, you know that when we drop things in real life, they don't just fall down with a constant speed. They start slow, but then they accelerate, and and they speed up as they fall down. And this is a physics concept. If you need some help, look up objects in free fall. Exercise 2 is going to be making a ball that's initially going to the right, and then it's going to slow down and start going to the left. Part 3 is a lot more physics involved. We're going to simulate a ball being thrown along an arc. So it's going to be thrown, let's say, in the positive x direction and the positive y direction, and then gravity is going to make it arc and fall down, just like if you were to throw a baseball in the air. And yeah, that's it for our exercises. Now let's move on to part 4, our feedback. This should be quick. Again, we have our weekly feedback form. Just fill it out. It should take 3 to 5 minutes. This could be anything you want to say. Comment on my music, comment on whether or not you like the dark mode, comment on whether you thought I went too fast, too slow, if you knew this stuff, literally anything. Everything you say is going to be taken into account, and there aren't that many of you, and there are even less of you giving feedback to me right now, so if you give me advice and you if it's honest, then there's a really, really good chance I'm going to implement it into my lectures, and you essentially have someone personally teaching you this stuff. And of course, if you're not on the Discord, join in and invite your friends. We're going to be having some meetings on there as well. So that's it. I hope you enjoyed, and I'll see you next week. Take care.